So at the end of our last class, we were talking about plugging x values or expressions into functions. Okay. And teach several classes of this, so I'm trying to remember exactly where we left off, but I think what I had done was we had just started to plug a plus 1 into this function right here. Does that sound familiar to everyone?
Very unsure.
Okay. So what we do when we plug anything into a function for the variable is we replace the variables. In this case, there's two x's. We replace it with this expression in here, or if it's a number, we replace it with that number. And to make sure we respect proper order of operations, we should put it in parentheses. So this is going to be a plus 1 squared minus 3 times a plus 1 plus 4. And it's possible whenever you do a problem like this, you might need to go off to the side and do a little bit of side work. So for instance, the first thing I need to do is I need to do this a plus 1 squared. Now a plus 1 squared is the same as a plus 1 times a plus 1. And however you learn this, whether you learn to FOIL this or if you learn to smiley face it, you got to make sure you do all the appropriate multiplications. So you got to do a times a, which is a squared, a times 1, which is a times 1 again, which is a, and 1 times 1, which is 1. So you get a squared plus 2a plus 1. Remember not to distribute the square. Then you're well on your way to simplifying this thing. And remember what simplifying means, everyone. In this problem, simplifying means you want to clear the parentheses, collect like terms, and then rewrite the equation in descending order. Descending order means so the powers get smaller as you go from left to right. So first I have cleared these parentheses by using the exponent. Now I'll clear these parentheses by distributing the negative 3. And then I will collect like terms. A squared minus a plus 2. And I'm done. So those don't need to be the end of the world. Just make sure you keep your work straight. Don't make up math rules that don't exist. And when they say simplify on this type of problem, that's what they mean. I always kind of thought it was the responsibility of the person telling you to simplify to tell you what they mean by simplify. So that's why I told you what I wanted you to do on this problem. Okay. Another detail that I want to talk about that you're going to see as you finish up your homework for 2-3, don't worry, we actually are going to finish section 2-3 today, is you'll see a problem that maybe is talking about finding the maximum or minimum. Now, you've probably all taken enough math courses that you know sometimes the most frustrating part of a math problem is knowing what they're actually asking you to do in the math problem. You can do the math, it's just the instructions look a little bit weird, or you're not quite used to the way they're asking you to do what they want you to do. So, you get to a problem like this, and it tells you to find the maximum. And you'll notice that there's a couple ordered pairs labeled on here. This one maybe is at -2, 5, and this one over here maybe is at 10, 5. And you'll notice that this particular graph has 2 peaks on it right here. So if it's saying find the maximum, maximum means the highest point. So you're like, okay, it must be those places that it wants. But when you see these, they don't necessarily ask for the ordered pair. They might ask something like this. Where does the maximum occur? And when they ask that, they're actually just asking for the x values. They want to know at what x values do we have those high points on the graph. So your answer would be this: x equals -2, comma 10. Not the ordered pair -2, 10, but you're just trying to say one of those maximums is at the x value -2, and the other one is at 10. And then it says, what is the maximum? And that's when you say y equals 5. So it's kind of saying, where do those high points occur, and then how high does it actually get at those high points? And we get so used to answering questions in either ordered pairs or interval notation, because we did a lot of interval notation last time, that we're just not always clear what they want from us. So when you're doing a question like this, and the instructions are like this, they might be trying to break it up into, first give the x values, now give the y value. So just read the instructions carefully and you should be just fine. Questions or comments about that? Okay. So, we're now done with 2.3. We finally got through our first section. And you can do, if you have not already, the build understanding questions from the homework. Just so you know, after section 2.3, we do move on to section 2.6. So 2.4 and 2.5 are skipped. So don't go nuts trying to find the homework for 2.4 and 2.5 because there isn't any. Sometimes people get alarmed because like, what happened to those sections? We just don't cover them in this class. That being said, we do need to do a bit of kind of a intermediary section right before we're ready to move on to 2.6. So before we move on to section 2.6, we're going to talk a little bit about lines. And I know a lot of you know all about lines because you're college algebra students, but sometimes it's easy to forget some things or get some things backwards. So first we're going to talk about vertical lines and horizontal lines. Both are very, very important in math. Vertical lines and horizontal lines are both very, very important, but only one of them is a function. What's a function? A horizontal line or a vertical line? Horizontal lines are functions, yes. And vertical lines, while they are not functions, are still important. So we don't ignore them, we just make the observation that they're not functions before we look at them. So there's a vertical line. And there's a horizontal line. And you can clearly see from the pictures that a horizontal line does pass the vertical line test. No matter how many vertical lines I draw here, I'll only hit this once. And we know a vertical line fails the vertical line test because you can draw a vertical line right on top of it. So let's write down a few things. The domain of a vertical line is just a single number. Doesn't really go left or right at all from there. It's just a single number. So whatever that number is right here, where it hits the x-axis, that's actually the domain, just one number, no interval. But the range, since it goes up and down forever, is -infinity to infinity. Come over here to the horizontal line. The domain of a horizontal line is -infinity to infinity because it goes left and right forever. But its range is just a single number, just a single y value. So the range is just a single number. Also, a lot of times when you're talking about lines in math, one of the things people want to know is the slope of the line. Slope is indicated by the letter m, mx plus b, slope-intercept form of a line. And so we need to know how to give the slopes of these things. Well, the slope of any horizontal line is 0. Absolutely every time the slope of a horizontal line is 0. And the slope of a vertical line is undefined. And that's the terminology we're going to use for the slopes of horizontal and vertical lines. We're either going to say 0 for a horizontal line, or we're going to say undefined for a vertical line. We should never say no slope, because it is confusing. If you tell me that a line has no slope, I don't know if you mean, does that mean it's undefined or does that mean the slope is 0? So we don't use that term, no slope. We either say undefined or 0 for horizontal and vertical lines. One of the things that confuses people most about vertical and horizontal lines is the equation, because the equation for a vertical line is x equals a number, and the equation for a for a horizontal line is y equals a number. Now people get confused because the x-axis is horizontal and the y-axis is vertical, so they kind of think about that, and then these things seem backwards. But the reason they're not backwards, the reason x equals a number makes sense for a vertical line is because every ordered pair has the same x value. Every single point on a vertical line has the exact same x value as every other point. So that's why when you say x equals a number, what you're basically saying is you're saying, I'm thinking of a line where every single ordered pair starts with the same number, this number right here, whatever it is. In fact, that number is the domain of the vertical line. And when we look at a horizontal line, it's y equals a number because every single ordered pair on this horizontal line has the same y value. So that's why it makes sense to say y equals a number. Every ordered pair has the same y value, which is actually also the range of the horizontal line. Another way you can kind of remember that and keep that straight, everyone, is because when we work with equations in a math class, when we work with functions, when we work with a function, what are we used to seeing? X equals or y equals? Well, we're used to the x being mixed in there. But all by itself on one side of the equation, we usually see a y. Y equals x squared. Y equals 2x plus 3. Y equals 17x minus 19. We're used to seeing that y because that's how most functions start. And that's also how the horizontal line, which is a function, starts. And so, the horizontal line only, not the vertical line, but a horizontal line, you might have some examples that are written like y equals 3 or y equals 17. But since it's a function, you can also see f of x equals 3 or g of x equals 17. But you're not going to see that over here. I can write something like, x equals 4, but I can't write f of x equals 4. Oh, it's conveniently already crossed out for me, because that's not a function. But these are functions over here, the horizontal ones. And the last thing I really want to say about these two things in general is this. Horizontal lines are constant functions. When you're doing your homework, they will sometimes ask, is the function a constant function? And a constant function is the same thing as a horizontal line. It means it's always the same. It's always flat. Not any line, but a horizontal line is also called a constant function. So when you are asked in the homework, is this a constant function? It's really saying, is this a horizontal line? So I want to talk about 4 very important lines. Not that all lines aren't important and awesome, but let's talk about 4 very important lines. 4 very important lines, 3 of which are functions. We'll start with the one that is not a function. And that is the vertical line that lies directly on top of the y-axis. The y-axis itself can be given as a line, not a function because it's a vertical line, but can be given as the line x equals 0. Because every single ordered pair on this line starts with 0. Look, up here is 0, 3. Here is 0, 1. Down here is 0, negative 2. They all start with 0. So if anyone ever says to you, what's the equation of the y-axis? The equation of the y-axis is x equals 0. So, what do you think the equation for the x-axis is?
Undefined.
The x-axis is y equals 0. Is this a function? Is a horizontal line a function?
Yes.
Yeah, it's also one of the constant functions because it's a horizontal line. But if you think about it, every single ordered pair on here ends with 0. Everyone ends with 0, y is 0. So if anyone ever says to you, what is the equation that actually, of the line that actually lies right on top of the x-axis, or is the x-axis itself? That's y equals 0. And the one that lies right on top of the y-axis, is the y-axis itself, is x equals 0. Those are important to know. Just knowing those two equations is really helpful. And I said we had 4 very important lines, 3 of which are functions, so we've looked at those. I wonder what the other 2 are. Well, let's take a look. Y equals x, or just f of x equals x. Sometimes in a math class, we get so involved with more complicated equations, more complicated functions, we get a little bit lost when we just see y equals x. We're like, what are we supposed to do with that? What does that mean? Well, it is a line. In fact, it's a very important one that's called the identity function. And the way it works is every single ordered pair on it has the exact same x value as y value. Check it out. It has the ordered pair 0, 0 on it, but it also has the ordered pair 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, negative 1, negative 1, negative 2, negative 2. Every single ordered pair on this sucker has the exact same x value as y value. It's a very important line, but sometimes when someone just says, hey, graph y equals x, you're like, wait a minute, don't you need to give me more information on that? What do you mean? No, it's this equation, this graph right here. Up here somewhere is 4, 4. So that's called the identity function. It has both a domain and a range of negative infinity to infinity. It goes left and right forever. It goes down and up forever. And since it's a function, it does have a slope, and its slope is 1. Up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1 forever and ever and ever. That's the identity function, everyone. And it has a friend. Actually, I don't know if they get along or not. I shouldn't say that they're friends. Y equals negative x. Or, since this is also a function, you can give it a function name also. Looks like that. Please forgive me, my line not being that straight. But the way this works is every ordered pair, x and y, have opposite signs. So if you have an ordered pair down here that starts with 2, it ends with negative 2. If you have an ordered pair up here that starts with negative 3, it ends with 3. So the x and y just have the opposite signs. If one's positive, the other's negative. If one's negative, the other's positive. But just like its friend, it does go from 0 through 0, 0. This one doesn't have a cool name. It does have a domain and range of negative infinity to infinity, both of them. And it does have a slope of negative 1. So what do I mean when I say these are important? Well, I mean you kind of want to know them. If someone says y equals x, you want to get this picture in your head. If someone says y equals negative x, you want to get this picture in your head. It's kind of like once upon a time you took an arithmetic class and they said everyone needs to memorize their multiplication tables up to 12. Because when you looked at 7 times 8, they didn't want you to have to think for a few minutes what it was. They just wanted you to rattle it off so you can move on to more important things. It's kind of the same thing here. We're going to be doing things that are more complicated than this. So I'm not saying this is easy, and I'm not saying you're fools if you didn't know this when you came in here today, but what I'm saying is you do want to learn these. Because as we do more complicated things, it will be very helpful to you if you just kind of know when you see y equals negative x, and I'm talking about this graph. And when I say y equals x, I'm talking about this graph. It will help you out a lot. Just to add those to kind of your memory and your knowledge about mathematics. Okay. So, how do we summarize this? What we're learning about lines. This is what we'll say. We'll say, if a line is a function, and it is a function as long as it's not a vertical line. Every line is a function except for the vertical lines. It can be written starting with f of x equals or y equals. So as long as the line's a function, you should be able to write it using function notation, f of x equals or y equals. And the domain is negative infinity to infinity. Every line has a domain of negative infinity to infinity as long as that line's a function. The only line that doesn't have that domain is a vertical line. Otherwise, every line goes left and right forever. The other thing we want to remember, if we forget every trick that we once knew about lines, we want to remember one thing, and that is this. You can draw any line as long as you know two ordered pairs on the line. If I give you a horrible line and I say I want you to draw this line, and you forget all the tricks you know about drafting lines, remember this trick. Plug in an x value, you get a y value. Plug in a different x value, you get another y value. You plot those 2 points, you have the line. Even if you don't remember all the fancy tricks like graphing by the intercept method or graphing using slope-intercept form, you get 2 points on that line, you win. So, section 2.6, there's quite a bit going on in this section also, but for the most part, it can be broken down into two major concepts. The first is piecewise functions. Functions, because they pass the vertical line test. Piecewise, because they are made up of several different pieces. Here's an example of what a piecewise function might look like, everyone. And do we agree that when you're doing a vertical line test, when you're drawing those vertical lines, that it misses at a hollow point? Do we remember that? Vertical lines miss at a hollow point. So, this is a function, because the two places where you might think it's not a function or fails the vertical line test, it passes because we go right through the hollow point. So what we have here is we have a piecewise function. We have a function made up of several different pieces. Okay. The other major concept that we're going to see in this section, is algebra's basic functions. And I know almost all of you did the homework, the pre-work for section 2.6, so you'll know what I mean. When I put these suckers up here. Those are our basic functions in algebra. We're going to talk about those today. Near the end of class, we'll get to them. But those are algebra's basic functions. f of x equals x squared, g of x equals the square root of x, h of x equals absolute value of x, p of x equals x cubed, and q of x equals the cube root of x. By the way, these letters are completely arbitrary. Tomorrow, I might put x squared up here and call it g of x. So don't let that bother you. I just wanted to pick 5 different letters to put them all up here at once. So you saw these when you did your homework. It asked you to pick out the right graph to match the equation. It asked you to give the domain, and we'll talk about these in a bit more detail later. But right now, we're going to do piecewise functions. But this is coming up later today and for part of the class tomorrow. So just a little preview there of what's coming up next. But now, we're going to do piecewise functions. So piecewise functions look very intimidating the first time you see one. Why? Because it's basically several different functions put into one. So instead of having just, y equals 2x plus 1, or y equals 3, or y equals negative x minus 5, 3 functions we might be comfortable working with, they've all been smashed together into one big function, the piecewise function. Depending on the math teacher that you have or the textbook you're looking at, after they give these 3 things over here that look like the right side of each of these equations, you might either see the word if, or the word for, or just a comma written here. It really doesn't matter what someone puts there, because you're going to do it the same way no matter what it is. So you might see if, you might see for, you might see a comma. Don't worry about which one you see there. And then what you're going to see over here for a piecewise function is you're going to see several inequalities. They might have some equal to's mixed in there, like that. Now that looks like a mess, and I agree that looks like a mess. And if you've never worked with one of these before, that's the kind of thing that makes you turn off the computer and say, I think I'll worry about this later. But my job today, one of my jobs, is to make it so you can see that these things are not too bad. And if you'll pardon the pun, we're going to rip them apart piece by piece and see that they're not too hard to work with. Let's talk about these over here first, these inequalities. What these are, everyone, is each one of these inequalities, much like interval notation, represents a piece of the number line, a chunk of the number line. For instance, this top one, x less than negative 3, here's the number line, here's 0, here's negative 3. It's talking about this piece of the number line, everything less than negative 3. This one right here, the middle one, negative 3 is less than or equal to x is less than 5, is talking about another piece of the number line. It's talking about from negative 3, including negative 3, all the way up to 5, not including 5 because of the equal to's, and the one that doesn't have the equal to. It's referring to that piece of the number line. And this one on the bottom, finally, is referring to this piece of the number line. And the first important thing I want you to notice is the piece of the number line that they're each referring to, they don't overlap at all. There's no overlapping. So this gets part of it, this gets part of it, this gets part of it, but none of them share any parts of the number line. Where they get close to each other, at one point, one of them will always, at least one of them will have a hollow point there, so they don't actually share any places. What this does, everyone, is it tells us how to work with the piecewise function. Normally, when someone gives me a function like this, g of x equals 5x plus 1, and tells me to plug a 2 in there, I just replace the x with a 2. 5 times 2, and I get my answer. When someone tells me to plug a number into this piecewise function, like this, f of negative 6, I cannot plug the negative 6 into all 3 pieces, because then I'll get 3 different answers, and if I get 3 different y's with 1 x, it's not a function. Does everyone agree with that? So what I need to do is I need to look here first. Start here. Because this tells you over here which one of the parts you're going to plug it into. You ask yourself, which part of the number line does negative 6 fall into? This top one, the middle one, or the bottom one? Which one does it fit into? The bottom one. Negative 6 is less than negative 3. It's over here somewhere. And that tells me that I plug it into the top part only because negative 6 is less than negative 3. Because this x value is less than negative 3, so it goes in the top one. And that's the only one I plug it into. 2 times negative 6 plus 1 is negative 11. And I'm done. I don't need to plug it in the other two. Not only should I not, but I mean, it's wrong if I do. I only want to plug it into the one part. So you are thinking kind of backwards, because you start here, and then you plug in over here, but only to the part that matches that inequality. So, f of 5. 5, does that work in the top one, the middle one, or the bottom one? Only the bottom one. You might think Steve doesn't work in the middle one and the bottom one. It only works in the bottom one because 5 is not less than 5. 5 is greater than or equal to 5. So this one works in the bottom one only. And plug that in there, I get negative 5 minus 5, or negative 10. So you use the inequalities to figure out which part you plug it into, then you plug it into that part only. Now normally we don't write these number lines over here, but I did that on this first example so you could see that's how these work. They're each giving you a piece of the number line where your x value could have come from. You find where your x value comes from, and that's how you know which equation to use. All right, now let's talk a little bit more about this sucker. F of 0. Now 0 works in the middle one because it's between negative 3 and 5. Does everyone agree that 0 is between negative 3 and 5? So we're supposed to plug it into the middle one, but let's talk about that because that messes with some people. This goes into the second equation. But this is what the second equation looks like. The second equation is y equals 3, which is a constant function. The result of plugging any x value into y equals 3 is just 3. If your equation is just y equals a number, or f of x equals a number, that represents a horizontal line. And no matter what number you plug into a horizontal line, you get the same y value back out every single time. So some people get upset because they're like, Steve, I want to plug a 0 into that middle equation. But there's no x to plug the 0 into. Well, that's not a problem because the answer is just going to be 3. In fact, if you take any number between negative 3 and 5, including negative 3 but not including 5, and you plug it into this piecewise function, you're going to be using the middle function. And when you use the middle function, what is your result always going to be? 3, every single time, because it's a constant function. It just gives you that number back. So, I know you can't see it. Recall, this is the interval we're working on. So no matter what I plug in there, whether I plug in a negative 3 or a negative 2, making sure I stay between negative 3 and 5, or a 1, or a 4, or a 4.9. Does everyone agree that negative 3, negative 2, 1, 4, and 4.9 all fit into this interval? And that interval corresponds to the part of the piecewise equation of f of x equals 3 or y equals 3. 3, 3, 3, 3, 3. If you plug 100 in, if you plug in 100, you're using the bottom equation again. If you plug in negative 100, you're using the top equation again. If you plug in 100, you get negative 105. If you plug in negative 100, you get negative 199. And I know you can't see the function anymore, but there's the top equation, there's the bottom equation. And there's our results. You can plug any number you want into this function. You just got to make sure when you plug in a number, you're plugging either the top, the middle, or the bottom, whichever one you're supposed to. That's how piecewise functions work. That's the way we make sure that they're still functions. Because if we plug a number into multiple parts and get multiple answers, it's not a function. Are we recording now? Yes, we are. All right. In Math 121, the class you're taking right now, college algebra, our pieces will always be linear. This is the introduction to piecewise functions, everyone. You take more math classes, you'll see more complicated piece functions that might look something like this. With curvy parts to them, we're not going to do that in this class. Ours are all going to be straight lines. So we don't need to worry about anything this nasty in this class. We will never have more than 3 pieces except for the greatest integer function. Those of you who did your homework encountered a exciting little function that looked like it was an x surrounded by kind of a weird pair of double brackets called the greatest integer function. If you remember, it looked like a staircase. That could be thought as a piecewise function with an infinite number of pieces, so that is one example, and we're going to have more. But for the most part, we will never have more than 3 pieces. So you're not going to see this in this class. I'm not going to do one of these to you. Because this would just take forever to do. And it's not going to be much fun to do that. So we're not going to see this either. Our piecewise functions, except for the greatest integer function, are going to be 2 or 3 pieces only. That'll be enough. That'll be enough to learn it. All right. So we will graph our first piecewise function. So we're going to graph a piecewise function. So we're going to start with one that's fairly straightforward. I put a piecewise function up here, and I've also put a grid up here so we can graph it. Now, when I see this piecewise function, I see, all right, we're going to have to deal with 2 pieces here. And I actually know what both the pieces are. If I look here, I know that I'm just going to be graphing the horizontal lines, y equals 4 and y equals negative 2. That's what these mean over here when I just see this number over here. So if I graph y equals 4, it's going to look like that. Please excuse my wiggleness. And if I graph y equals negative 2, it's going to look like that. But that can't possibly be the answer because this is not a function. It fails the vertical line test. Because no matter where you draw a vertical line, you're going to hit both of these horizontal lines. So this is not it. So this part over here tells you what you're going to draw. This part over here tells you where you're going to draw it. So if I look at the top part, g of x equals 4, if x is less than or equal to 0, that tells me that this piece should just be 0 and negative x values. So I actually don't want the entire graph of y equals 4. I just want the part where the negative x values are. And where are the negative x values? The negative x values are over here. So what I'm going to do is I'm going to erase the part of the graph that I don't want. Just like that. It's gone. And then I say, what happens at 0? Well, I notice that there is an equal to here, and an equal to tells me that there's going to be a solid point. So that's part of it. Then, I see for this bottom one here, I'm supposed to have positive x values. Only the positive x values. Well, those are over here. So I erase the part that I don't want. And then I notice that there's no equal to, x is greater than 0, so that's going to be a hollow point right here. Is this a function now? Does it pass the vertical line test?
Yes.
Yeah, and it's the correct piecewise function. Why? Because I drew what I was supposed to draw, and I only drew it where I was supposed to draw it. And when you get better at these, you don't need to use the erasing technique. You can just draw the part you need right off the bat. But I find for the first example, it works well to kind of draw the whole thing and say, let's get rid of the part we don't need. So we're done. The graph is just the blue part you see here. The green part was just me circling the positive and negative values. We can go ahead and erase those too, though, so we don't get confused. There we go, done. And we learned something too. We learned that when we're drawing these, if we see the equal to's, that's going to mean we're going to be using a solid point. If we don't have the equal to's, that means we're going to be using a hollow point. So what we have here is we have two horizontal lines that each got a piece of the x values. Neither of them got all the x values, they each got part of the x values. And that's why we have a function. And that's our first example of drawing a piecewise function. We're going to do another one. That cool, everyone? Let's do one that's a bit more exciting. A bit more exciting. All right, I'm going to need another graph in here. This one we'll do a 3-1. We'll do a 3-piece one. So we got h of x equals, I do -5, 2x plus 1, and x. And there might be an if there might be a for, there might be a comma, it doesn't really matter. And this one looks a little bit worse just because there's 3 pieces and they're not all horizontal lines. So yeah, this one is going to be trickier, but we should do a trickier one. You know, there's really no way you could graph a piecewise function unless you know independently what each piece would look like. So when I see this, I think it's basically going to be these 3 graphs, or a piece of each one of these graphs sharing the same coordinate system. So I'll have a piece of y equals -5, a piece of y equals 2x plus 1, and a piece of y equals x. But do I know what those look like individually? Well, I know what y equals -5 looks like. 1, 2, 3, 4, -5. It's just a constant function. It's a horizontal line. I can draw a piece of that. I know what y equals x looked like. That was one of those functions I said that was kind of important to know. The identity function, just that perfect diagonal line right there. I know that one. I can draw just a piece of that. This one, y equals 2x plus 1, maybe I don't always have that graph running around in my head, but I do know I can find 2 ordered pairs on it. Does everyone agree with that? I can plug 2x values and get 2 ordered pairs. Or, if I'm feeling a bit more comfortable, I know that it has a y-intercept of 1 and a slope of 2, so I know it looks roughly like that. So here's what I need to do. I need to take a piece of this one, a piece of this one, a piece of this one, and put those 3 pieces all on the same coordinate system, so it passes the vertical line test. All right. Now, I think that the first one is going to be the easiest to do, because it's just a horizontal line. I just need to make sure I draw it in the right place. Well, it's for values less than or equal to -3. Well, here's -3. So it's going to be to the left of that. Come down here to where -5 is, and so it's going to be Now, I haven't decided if I'm putting a hollow point or a solid point on that yet, but how does that look so far, everyone? It's y equals negative 5. Does that look okay? Just part of it. Then I come up here and I notice that there has an equal to on it. So it's going to be a solid point right here. That horizontal line at y equals negative 5 exists for all values less than or equal to negative 3. I don't go all the way across because this inequality up here tells me that I have to stop when I get to negative 3 on the x-axis. This stuff is tricky. I promise you, if you're thinking you're the only one that's confused, you're not. But there are also some people that are going to get it really quickly, and that's awesome too. But if you are confused, it's not a bad thing, because it happens to a lot of people on these. Are we okay so far? Let's do the bottom part next. Let's do this one next. Now I know what y equals x looks like. It looks like this, roughly. But I don't want to do that whole thing. You shouldn't do that, but I have an undo button, so I can do that. I only want part of it. But at what x value does that start? Where should I start? At 2. But remember, I'm starting at 2. I'm starting this diagonal line at 2. So I need to make sure I start at the right y value also. Does everyone agree with that? So I start right here. And normally the graph y equals x goes forever, negative infinity to infinity. But this time, because it says right here x is greater than or equal to 2, it stops right here, because that's where 2 is. And how do I know to start up here at the y value of 2? Because if I take a 2 and I plug it into this function, I get a 2 back out, which is the y value. That's how I know. It's just a piece of the identity function. All right, now this next part is very, very sneaky. I need y equals 2x plus 1 between negative 3 and 2. Now, 2 points are enough to graph any line. If I can find 2 points on this, I can graph this piece. Here's the really slick part. You can plot hollow points just like solid points. Now everyone, this inequality right here does not have any equal to's in it. It just is less than and less than. There's no equal to there. So that means I'm going to be using hollow points. Does everyone agree with that? But I can actually still plug those end numbers in of negative 3 and 2 as long as I know that what I'm getting back is a hollow point. Like this, watch. If I plug negative 3 in, then what I do is I do 2 times negative 3 plus 1, which is negative 5, which means that I can draw a hollow point at negative 3, negative 5. Not a solid point, but a hollow point. And if I plug 2 in here, 2 times 2 plus 1 is 5. I can put a hollow point at 2, 5. For those of you who don't like that, I'll show you something else here in just a moment, but bear with me for a second. So I come up here and I make my hollow point and my other hollow point. So one of my hollow points is actually right here. Actually, I was going to do this in a different color. I'll do this in blue. One of my hollow points is right there on that solid point that already exists at negative 3, negative 5. And the other one's up here at 2, 5. Now you might say, Steve, how can you do that? You're plugging numbers into that you're not supposed to plug in. Well, you can plug other numbers if you want also. You can plug some numbers in between negative 3 and 2 and plug them in there. What's the number between negative 3 and 2, everyone? Give me a number between negative 3 and 2. 1. If you want to plug a 1 in there, that's fine. If you plug a 1 in there, you'll get this point right here. If you plug a 0 in, you'll get this point right here. If you plug in -1, you'll get this one. If you plug in a -2, you'll get this one. You can see they all lie on the same line. The reason I like to use those hollow endpoints is those show me where to stop. Because if I just did these points, these valid points, which are solid, and connected those, and just did that, then I'm not showing everything. But if I do the hollow points, then I can go all the way to the ends, and I get a correct answer. That's it, everyone. One little detail. In Math 121, a solid point covers a hollow point. Some of you may have taken a class before where they made you do this little circle around the point. We actually don't have to do that in here. You can just put one solid point there, and that takes care of it. Because the solid point just covers up the hollow point. So even though this thing has 3 pieces, 2 of the pieces are actually touching. Yeah, question?
Would you prefer us to do the solid point, or does it matter?
If you're more comfortable doing the solid with the hollow, you can do that on there. But I'm just saying you won't see that on the homework. But yeah, if that's the way that makes more sense to you, then you should obviously do that, because that's not wrong to do that.
And is that point still considered a function?
Well, it is, because it's a single point. It's a single point. It just happens to belong to the first part of the function, not the second part of the function. And there's still a hollow point there, but the way we draw it, the solid point is covering the hollow point. So this is a function, everyone. This is a piecewise function. We do okay? Takes a while to do them, but you can do them. But you're not going to have very much fun doing these. Well, some people don't have fun doing math, but let's say you usually have fun doing math. You're not going to have much fun doing these unless you know what these look like already individually. You can't put something together unless you know what the different parts are like. All right, let's try something slightly different here. But first I have a few notes for you. What if you are given the graph and you need to write the equation? Well, that's a pretty good what if, because that's about to happen. The first thing you want to do is decide if you have 2 or 3 pieces. Are you going to be writing something that looks like that? Or are you going to be writing something that looks like that? 3 different pieces or 2 different pieces? Because when you write these equations, one of the things that makes it tricky is you're responsible for both the equation part and the inequality part. That's why it's tricky. As you move left to right on graph, the equation moves top to bottom. That way we keep our inequalities in order. But in other words, what's happening, everyone, is let's say you have a 3-piece one. This will be where you write the equation for the left piece, the middle piece, and the right piece. So you do want to make sure you write them in the right order. As you look left to right on your graph, you're listing your equations bottom to top. And then, of course, you'll have the inequalities over here that go with those pieces.
Top to bottom or bottom to top?
Sorry, top to bottom. Top to bottom. I'm sorry if I said bottom to top. I was thinking of range. Yeah, top to bottom. What else do we need to know to write these equations? Well, remember, if the piece is a horizontal line, you just need the correct number. Remember, the equation for a horizontal line is just y equals a number. It's just y equals a number. And with a piecewise function, you already have the f of x equals over here. So you just need to figure out the right number to write in, if it's just a horizontal line. Maybe a piece is y equals x, or y equals negative x. Maybe it's one of those basic functions, the identity function or its friend. And if that's the case, you also luck out, because if it's just one of those perfect diagonal ones, either y equals x, y equals negative x, then you just need to write x or negative x in for the equation. It's very fast. That's one of the reasons it's good to know those equations. Here's the tricky one. If the piece is not horizontal, so it's not just a number, or y equals x, or y equals negative x, you need the slope and the y-intercept so you can give mx plus b. If it's not just a horizontal line, and it's not just y equals x or y equals negative x, you better identify what the slope and the y-intercept is. That way you can write the equation for that piece. And that's what we'll focus on, is how do we do that. Finally, when you're writing these equations, the inequalities come in three basic forms. And I'm going to write them without equal to's, but they may have equal to also. But when you write the inequalities off to the side to say where you're graphing that piece, they're going to look like one of these things. You're either going to have x is less than a number, x is between two numbers, or x is greater than a number. Graph is left of b value on x-axis. Graph is between b and c on x-axis. Graph is right of c value on the x-axis. That's it. Either it's smaller than a number, bigger than a number, or between two numbers. And maybe, as I said, this might have an equal to on, or one of these might have an equal to, or this might have an equal to. But those are the basic forms you're going to use. We're not using the interval notation here. We're using inequalities to express a piece of the number line. Are you ready to try one with Steve? Let's do this. Let's see what we can do together. It's not always the most fun, but we'll do it. We'll use these rules. These rules, of course, if you didn't get them all down now, will be posted after class. That way you can use them when you do your homework and give them a good study. All right, piecewise, this one is the one I want. Copy. Okay. How many pieces? 3 pieces. All right, start big. 1, 2, 3. Now, one thing that helps me when I'm doing these is my job is to come up with the right equation, which means I can make as big of a mess over here as I want if it helps me. If I need to write a bunch of notes on this graph, I should go ahead and do it. So the first thing I'm going to do is say this is graph 1, this is piece number 2, and this is piece number 3. Why? Because left to right, top to bottom. All of these 3 pieces, 1, 2, and 3, which one looks like it has the absolute easiest equation? 3, because it's a horizontal line. Everyone agree with that? If it was allowed to keep going, it would hit the y-axis at what number? 7, so that's its equation. 7. If, well, where does it start? At the x value of 1. So it's for all values bigger than 1. Should it have an equal to?
Yes.
Why?
Solid circle.
Solid point. Good. Oh, I'm 1/3 of the way done. Why? Because I recognized a horizontal line. I recognize that the equation for that was just f of x equals a number. Notice that I don't write y equals 7 here, because we already have the f of x equals over here. So you just need the right side of the equation, just the 7. Okay. We're going to look at piece number 1 right now. Do you recognize piece number 1?
Yes.
Yeah, the opposite.
Yeah, so what is the equation for that one? Just what would the equation be for it?
Negative.
Y equals negative x. So what is the only thing I need to write here, because we already have f of x equals? Negative x. Got it. Where is it? Well, it's for all values. Well, I know that negative 2 is involved somehow. Is it for all values bigger than negative 2 or smaller than negative 2?
Smaller.
Smaller than negative 2. Should I put an equal to on it?
No.
Why not?
Comes in a highlight.
It's a hollow point. Pretty slick, right? Does it help to draw over your graph? I think it does. Let's look at the middle piece. Now, the middle, I'm looking for this, mx plus b. First of all, where does that middle piece, it might be hard to see, I know if you're sitting in the back row, but can anyone see where that middle piece hits the y-axis? Yeah, it actually hits it right here at 1. So that is going to be our b value. Then, see if you can figure out the slope. This is how I do it. 1, 2, 3, 1. 1, 2, 3, 1. 1, 2, 3, 1. The slope appears to be up 3 over 1. What's the easier way to write that? 3. And I'm between, don't worry about the equal to's right now, but I'm between what two numbers?
Negative 2 and 1.
Negative 2 and 1. Do either of those get an equal to? Which one? The first one or the second one?
First one.
First one, good. We did it. We just got to take our time. Use the graph. Don't try to do it in your head. Make a mess of the graph if you need to. But you can do these. One thing I do want to point out that's dangerous is it's amazing when you're on your own doing these problems, how you can forget what these inequalities do. And you start wondering, wait a minute, this was the correct answer, but you start thinking to yourself, well, is it that, or should it be this? Or should it be this? Or should it be this one? And then you just start getting all turned around, and you're like, which one of these is? I guess the top two are the same. Sorry, but you're like, it's not these. It's amazing how easy it is to mess those up. Negative 2 is the smallest. X is between negative 2 and 1. This is the correct way. If those inequalities are facing other ways, it's not right. Do we feel good enough about this one to try another one together?
Yes.
Cool in the back, cool up here, middle, front. See what we can do. Let's see what kind of damage we can do to the next one. Oh, Piecewise. So much fun. Let's see here. Copy. Edit. Paste. Here it is. This one is trickier than that one. That's why I'm doing this one next. No sense in just doing the same type of example all over again, but this one is also 3 pieces. So I'm making sure I give myself plenty of room to write all 3 pieces. Now, of these 3 pieces, which I could call 1, 2, and 3, which one, just at a glance, is going to have the easiest equation? 2. It's a horizontal line. So we know that the equation for this one is just y equals a number, in this case f equals a number, and since this is a piecewise, I just need to identify the number. Where is this piece hitting the y-axis?
-5.
Negative 5. Awesome. And I can easily see which values it's between. it's between -4 and 2. So as long as I can keep my inequalities correct, that's no problem. Now, do I need an equal to on one of those?
Yes, the first one.
Yeah, the first one. Okay, good. You know, while I'm here, while I'm doing this inequality, and I'm sort of in the inequality mindset, I think I'll do the inequalities for the other two pieces before I even come up with their equations. Because for the third piece, I can see it's at 2, and all values bigger than 2. Does everyone see that? So for this line here, I just go x greater than or equal to 2. And for this first one over here, this guy right here, I can see that it's -4 and smaller than that, not including -4 actually. So it's just going to be x less than -4. Some people find it easier to do all the inequalities first. Some people do all the equations first. Some people do the equation and the inequality that goes with it and make their way down the line. There's not a wrong way to do it, as long as you remember to work left to right, top to bottom. So make sure you write them in the correct places, but I don't care what order you fill in, basically, the 6 answers you're doing. This is the tricky part. Those other two pieces, neither of them is a horizontal line, and neither of them is y equals x or y equals -x. So, for 1 and 3, we need mx plus b. Here's the problem. Neither of those actually hits the y-axis. So it's much trickier to give the y-intercept. Do I see a hand up? Did you have a question? Okay. So what we need to do is this. If the piece kept going, where would it hit the y-axis? And you have to be very careful when you do this, everyone. But look at this up here. I can see that piece number 1 is going down 1 over 1, 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 down 1 over 1. Don't just rely on your staircase. Actually finish it. Once again, can I draw all over on this graph if I need to help me? Yeah, I can do whatever I want. And I can see where it hits. Now that actually doesn't happen on here, but it doesn't matter because that piece that we see up here, we're trying to come up with the equation if it was the entire graph. So the equation does not change when you just look at a piece of it. The inequality decides which piece we're looking at, but the equation doesn't change. So if this kept going, it would hit the y-axis right here at 3. That's how I know that piece has a y-intercept of 3. And I actually already figured out the slope too, because I was going down 1 over 1. So the slope is -1. So you can either write -1x or just -x, whichever one you prefer. Do you think we can do that same thing with the other piece? We can, yeah. So look what I do here, everyone. I'm going to kind of identify the slope first. It looks like it has a slope of 2, because I'm going up 2 over 1, up 2 over 1, so I'll write that in. 2x, that takes care of the slope. Now I need to figure out where it would hit the y-axis. And you see the way I did that, it's actually kind of hard to identify where the y-intercept is. That's why you don't just make the staircase, you actually finish the graph. There it is. 0, -4. -4. Make a mess of the graph. Do whatever you need to do to this graph. Color it with colors. Do whatever you need to do to figure out what those pieces are. You're looking for the equation as though the whole graph was there, not just the piece. This part, the inequalities, that takes care of the piece. That takes care of the piece you're looking at. This over here should be the equation as if the entire graph was there for your enjoyment, for your mathematical pleasures. If the piece kept going, where would it hit the y-axis? That's your B. use 2 points to find your M. And we win. Okay. Now, a lot of people see these and they're thinking, that's not enough. And I know that's not enough, which is why. Now, I said this in the beginning, I'm going to say it again. Follow the YouTube link on D2L for 5 more equation to graph examples and 5 more graph to equation examples. I love this stuff, and if I had time, I would just keep doing examples for you, but since I don't have time to do a dozen examples in class, I had to make videos of them for you to watch later. But they're narrated. It'd be just like watching this video after class. And there is also a worksheet with answer key for you to practice some more. So this is not your only resource. So if you are thinking after today's lecture, that was starting to make sense, but I can't believe you only stopped after that few examples, watch the videos and you can see some more. You can rewind them, watch them again, watch parts of it over and over again so you can practice with these things. Because that's all the time we have for doing them in class today. Everyone okay with that? Okay. All right, so the other big chunk of section 2.6 are the basic functions. And because we have other stuff we like to look at in this class, we don't have time to go over them all one by one, but we will talk about some of the highlights of them, of course. You know, I would never want to hurt anyone's feelings. That's one of my main goals when I'm teaching math, is I don't want to make anyone feel bad. So let me just explain what I mean by, go away, you stupid blue dotted line. All right, let me just explain what I mean by basic. Basic does not mean easy. It does not mean you're a fool if you came in here and did not know what these were, or I can't believe you didn't know about these before you took this class. What they mean is important. It means the functions we use a lot. It means just like y equals x and y equals negative x, and x equals 0 and y equals 0, I want you to get to a point in college algebra. One of your goals in this class is to get to a point so when you see any one of these 5 equations, you get the picture of the graph in your head. You know that graph. So when I start talking about y equals x cubed, you think of this graph. That's where we want to get. Because even though section 2.6 is about these graphs, in section 2.7, we start working with them a lot more, and you can't work with them if you don't know what the individual graph looks like to start with. So let's talk about them a little bit. You've seen these pictures and these equations when you did the homework, but let's talk about them a little bit more. You'll notice this first function right here. This is sometimes called the squaring function or the basic quadratic. That is awful. Or the basic quadratic. We'll learn more about that word quadratic in our next unit, but this is sometimes called the squaring function or the basic quadratic. This is called the square root function. The big letter V here is called the absolute value function. This is called the cubic or cubing function. And this is the cube root function. Abbreviated. Okay. What do we know about these? Well, we can identify the domain and range by looking at the graph. For instance, the basic quadratic or squaring function has a domain of negative infinity to infinity, but a range of 0 to infinity, including 0, because it only exists on and above the x-axis. The square root function, which looks like this graph fell over and died, and half of it's underground, you can't see it anymore, has both a domain and a range of 0 to infinity. Why? Because it only exists to the right of the y-axis and above the x-axis. This one has a domain of negative infinity to infinity, but just like its friend, the squaring function never goes negative. And in the interest of room here, I'll just write the domain and range of both of these is negative infinity to infinity. That goes for both of them. Not only is it important to know the shape of the graph and the equation that goes with it, but you do need to know something about the internal structure. And by that, I mean it's a good idea to know several ordered pairs that make up each graph. I'm not talking about giving you a test question where I say list 100 ordered pairs in the graph, because that's just a waste of time. But it's a good idea to know maybe about 5 ordered pairs. So what I've done here, and you can't see them all right now, and I apologize for that, is I have listed kind of 5 key ordered pairs that show up on each one of these graphs. One thing that's kind of fun to notice is that all of them have the ordered pair 0, 0, 1, 1 on them. That's kind of fun. But knowing these ordered pairs for each one of these functions, you'll be able to look at this as one big page after class. But knowing each one of these, knowing the 5 ordered pairs on each one of them really helps you understand the structure of the graph. One thing that bothers people is this function right here, because they're like, how is that a function? Because some people, and it's okay for one of these people, because I'm going to explain why this is not the case, some people think when I take the square root of a number, don't I get a positive and a negative root? Don't I get 2 answers? But please remember that the square root function means only the principal or positive square root. So when you plug a number in there, like 16, the answer is not 4 or negative 4. The answer is just 4. That's why this is a function. It doesn't give you the positive and negative, it just gives you the positive. Or if you put in a 0, you do get a 0 out. Where that plus minus comes from, that some people seem to think should be there, is when you ask this type of question. If you, instead of saying, what's the square root of 16, you say, what number do you square to get 16? This has 2 answers, because you, the mathematician, you apply the square root property. And you are the one that writes the plus or minus there when you apply the square root property, and that's why you get 2 different answers. It's 2 different questions. So class, everyone listen. What is the square root of 25? 5. What numbers could you square to get 25? 5 and negative 5. You see the difference between the 2 questions? That's why the square root is a function. It only gives you the positive one. Now the other words I'm going to throw up here, and I'm going to explain to you what they mean in a second. I'm going to throw them up. Is talking about the symmetry of these graphs. And we'll talk about symmetry in just a moment, so just bear with me for a second with these words. We call this graph an even function. We call this graph an even function. We call this graph an odd function. We call this graph an odd function. And we say that this one is neither. And when you start throwing around the words even and odd for functions, it's talking about how the function is symmetric. So, if you will allow me, I'm going to bring up a couple images here. New page. Copy. All right, here's an example of 3 even functions and one that's not an even function. It's not an odd one either, it's just neither. Even functions mean even means symmetric about the y-axis. Here's a good example. Most of us when we were kids at some point made a Valentine for someone, either in school or because we thought someone was special. And we took a red, pink, or a piece of paper and we folded it in half and we cut out half the heart and then we opened it up and we had a whole heart. Why? Because they're symmetric over a straight line, a vertical line. You can take any of these even functions, fold them on the y-axis, and they look the same on either side. It's a mirror image over the y-axis. That's what makes a function even. But it has to be the y-axis. You might see this w over here, which does have some symmetry to it, but it's not with the y-axis that it's symmetrical. So that's why that one's neither. So you wouldn't say to someone, this W shape isn't symmetrical at all. You just say, this particular one is not symmetric about the y-axis, so it's not even. That's why, if you'll allow me to go back for just a moment, both this graph right here for the x squared function and the one for the absolute value function are called even functions, because they both can be folded on the y-axis. All right. Odd's a little trickier. That's why we always start with even. Because odd functions are symmetric not over the x-axis, not over the y-axis, but symmetric about the origin. They're symmetric over a single point. And this gets kind of wordy to explain to people, but the way I kind of say it is kind of whatever's going on up in one corner, the opposite's going on in the other corner. So you want to reflect it not over a line, but over a point. So you can see this guy down here, like this. Well, then up in the opposite corner, in this corner, we have, all right, so yeah, like a wrestling match. And same thing going on here. You got something going on up here. You got this piece up here, and then you have its reflection down there in the opposite corner. I put a neither one on this one also. That's neither even or odd. That's just a mess. I don't know what that is. And most people can picture the even one really, really well because they just think about the, the folding the paper example or folding it in half. So, a friend of mine who I teach with, Debbie Martin, came up with a really good example to explain odd symmetry to people. This is pretty cool. How do you explain this? Ah, so big. How do I get this way? Here's the king of spades. And if you look at this little button right here, you can see that you can't fold the card in half vertically or horizontally and get an exact mirror image, but you can see kind of the spade up here and the spade down here, and you have the tip of his sword up here and the tip of his sword down here. So that's kind of where you see odd symmetry in real life. It's symmetric on a single point. Yeah, question?
You could also, I was going to say you could also spin it.
Yes, you can also spin it. It actually turns out, and we'll talk about this more in section 2.7, that's a great point, kind of if you reflect it twice, if you do 2 different mirror images, you get back to where you started. So yes, that's another way of thinking of it. 2 mirror images, if you do the top to bottom, and then right to left, you get back where you started. Good point, well done. Yes. All right. Last thing I want to say today is this, because I have 90 seconds. I can take my time. Absolute value function looks like a big letter V. You know that because you did your homework. Check this out. The absolute value function can be written as a piecewise function. Now, why you would do this, except as an exercise in how cool math is, some people might wonder that. But If you recall, y equals negative x looks like this, and y equals x, yes, it's still 748, look at me go. Y equals x looks like that. So, if you get rid of this piece here by just saying I want to look at x less than 0, and over here you say I just want to look at x greater than or equal to 0, so you get rid of this piece here. You stick a solid point on this one, because we have the equal to. You stick a hollow point on this one, and you put them together, and glory is ours. That's right, everyone. What an amazing way to end today's lecture, seeing that one of our 5 basic functions, the absolute value function, can in fact be written as a piecewise function.